Okay, good morning, everyone. Welcome back. I hope you had a good weekend, and I hope you're continuing to keep your spirits up during these challenging times. So, if you can hear me okay, please type yes into the chat window. Okay, great. Thank you very much. All right, gang. So, we're going to continue in chapter 12 today. In fact, through the rest of the week, that's going to be our emphasis, talking about the nervous system and nerve impulses. Before we do, though, I wanted to also reiterate, if you had missed my previous email, that your lecture exams from last week are in fact finished. The grading is finished. And if you haven't already done so, please log into the ClassMarker website to check your final score. As I mentioned, any small grading areas associated with using the computer, such as misspellings or having alternative forms of a word, in other words, using the singular version instead of the plural, all of those things were corrected and the credit was awarded back to you. So if you do have any questions about that, please let me know. Please send me an email. Let me open up at this time for you. Do you have any general questions about the exam at this moment that you would like to ask? Please feel free to do so, to unmute the microphone or talk in or type into the chat window. Is there anything about last week's exam that you have a question about? Pam has a question about the essays. How are we supposed to answer it? Well, on the computer, Pam, you always have a window that you can type your answers into. And I think, perhaps that was part of the confusion, but there'll always be a window for the student response. And so you type your answer into the window. If your answer requires you to answer multiple questions, then you have to specify in the window which question you are actually answering at any moment. So for example, for a fill in the blank paragraph, you would have to type in number 1, then your answer, number 2, then your answer, number 3, then your answer. That's how it will have to be moving forward for the rest of the semester. Okay, other questions? Okay, I'm getting a question about the anatomy aspects of the word bank. And let me just mention at this time, I can certainly help you and talk to you about that during the office hour after class. I will also say that most of the anatomy that you're asking about, Jennifer, is actually in the visible body. So it might be a situation where you're just not finding it at this moment in time. So I can help you with that. Okay, anything else? All right, gang, let me bring up the Excel spreadsheet again and talk to you about updating your course grade calculations because we are getting close to the end of the period of time where you could potentially withdraw from the course if you choose to do so. Now, I don't want any of you to do that, but for some of you, that might be the best course of action depending on what your grades actually are. Okay, so let me go to the computer screen here and bring up the Excel document. Okay, so you should be seeing an Excel spreadsheet at this time. And let me minimize things here. Okay. All right, so once again, if you did want to calculate what your course grade currently is, you would set up a spreadsheet matrix like this at your house, or you could do it manually on a piece of paper with, a pencil and a calculator. That would be okay. You would want to write down every exam score you've gotten so far. Lecture exam 1, the class average was a 58%. Lecture exam 2, the class average was a 66%. Lab exam 1, the class average was a 63%. Lab exam 2, the class average was a 74%. So obviously you would put in your own personal scores into this matrix. Whatever your personal grades were, that's what you would use. The weights of the exams are listed on the front page of your syllabus. Lecture exam 1 is weighted at 13%. Lecture exam 2 is 16%. Lecture exam 3 is 14%. Lab exam 1 is 13%. Lab exam 2 is 15%. And lab exam 3 is 15%. Okay. So the only two pieces of our equation that you don't have yet are the final exam, which is lecture exam 3, right? Lecture exam 3 is your final exam. And that schedule has not yet been released, but as soon as I have it, I will tell you. So the final exam schedule should be coming out very, very soon. So lecture exam 3 is the final exam, and you're going to have to make an estimate of what you think you could do on that exam. So for the final exam here, I'm going to make an estimate of 74%. For lab exam 3, which is the nervous system anatomy, you also have to make an estimate of what you think you can score on that. So for this, I'm going to say an 80% as my estimate for our calculation. What you do then is you take every score in column B and you multiply it by the corresponding weight in column C to give you the weighted scores. Okay, so that would be, and then you do that down every row. I do that for row B, for row 2, row 3, row 4, row 5, row 6, and row 7. Now, when it comes to your homework, you can earn up to a total of 14% of your course grade. So if you got credit for everything before our break, you will continue to get credit for everything after break. So that would be a maximum of 14% that you could earn. So the final grade in this hypothetical calculation would in fact be the sum or the total of all of these weighted scores added together. Okay, so it's giving me the wrong calculation. I want the sum of these things. So I'm going to add them together, and boom, for this hypothetical student, this student would be ending up with a 74%, which is a pretty firm C in the course, and that's what you would finish the semester with. So you need to do these calculations for yourself, so there's no mystery moving into the final exam. You know exactly where you're positioned and how well you need to do on the final 2 exams of the semester. At this moment, do you have any questions about how to calculate this? Okay, not hearing anything. By all means, if you are having trouble, send me an email and we'll work through that together so that you know where you stand moving into the final weeks of our time together. Okay, so I'm going to close that up, folks. Okay, and one more time before we start more content in chapter 12. Do you have any questions? Are you folks doing okay? How's your families at this time? I know there's a lot of stress out there. Everybody's feeling it right now. Okay. Okay. Well, feel free to stick around after class, during the virtual office hour if you'd like to chat. Oh, Pamela, I'm very, very sorry to hear about that. Okay. All right. Yes. I'm very sorry. My condolences to you. I have good friends in New Jersey, married couple, and at least the husband of that partnership, the husband's mother in New Jersey, did pass away from coronavirus last week. So, definitely starting to encounter circumstances where I personally know people that are impacted by this, and I'm sure many of you are as well. So I'm very sorry to hear that, Pam. These are very, very harsh times. Okay, let's see what we can do to make sure that you have every bit of possible preparation to be ready for the final exam in just a few weeks. So let's continue with chapter 12. All right, here we go. And at this moment, you should see a Microsoft Word document. And what I have up here are notes from last class, right? We were talking about neuroglia, the central nervous system, at the end of last class. And I had defined number 1 as the astrocytes and gave you some characteristics and features of the astrocytes. Okay. So right now we're going to continue with those notes and then move into the topic of the electrical system of the nervous system. So for right now, if you want visualization in your textbook, please be looking at page 411, figure 12.6, page 411, figure 12.6. Okay, and let's continue. Okay, the second type of neuroglial cell that we're going to document are the oligodendrocytes. Okay, the oligodendrocytes are responsible for forming and maintaining the myelin sheath around central nervous system axons. Oligodendrocytes are responsible for forming and maintaining the myelin sheath around central nervous system axons. Okay, you may have been you may have read more introductory material in previous courses that mentioned that the myelin sheath is only found in the peripheral nervous system. Well, that's not a bad statement, but it's not 100% technically correct. There can be some limited amount of myelin sheath actually found in the central nervous system, and the amount that is found in the central nervous system is actually formed by specialized cells called oligodendrocytes. You see that on figure 12.6 as the second term on the left side of that picture. Number 3, microglia. Okay, microglia is also a neuroglial cell. Okay, microglia function as phagocytes to remove waste and potentially harmful microbes that are invading the body. Microglia function as phagocytes to remove waste and potentially harmful microbes, bacteria, in some cases virus, that are invading the body. Okay, so just try to put an eye on these terms. You can see from figure 12.6 that the microglial cell does in fact look considerably different from an oligodendrocyte. Okay. All right, number 4 are the epidermal cells. Okay, epidermal cells are in fact a type of neuroglial cell. And what's significant about the epidermal cells is that they line the ventricles of the brain. Okay, so the ventricles of the brain, you're getting exposed to some of that anatomy during your study time with the nervous system anatomy vocab list. Okay, these cells line the ventricles of the brain and the central canal of the spinal cord. Okay. Okay. The function of these cells is absolutely critical. The ependymal cells that are in the ventricles and the central canal of the spinal cord, they actually manufacture and circulate the cerebrospinal fluid. Okay, now we haven't talked about cerebrospinal fluid all that much here, but you are certainly aware of it and you appreciate that the cerebrospinal fluid helps cushion and protect the brain and spinal cord from physical trauma. It also acts as a solvent to deliver nutrients into the nervous system tissue and remove metabolic waste products. Okay, so there's a lot of important features of the cerebrospinal fluid. That cerebrospinal fluid is in fact made by these ependymal cells. All right, a third thing I'd like to mention is that the ependymal cells, my software will work here, is these ependymal cells form the blood cerebrospinal fluid barrier. Okay. So you might be familiar with other courses or other topics. There are things called the blood retinal barrier in the eyeball, which protect the delicate retinal cells of your eye from potential toxins and poisons. There's also the blood-brain barrier that acts to protect things from crossing from the bloodstream into the brain. There is also the blood cerebrospinal fluid barrier. Okay, the ependymal cells form that barrier to prevent anything that's potentially harmful in the cerebrospinal fluid itself from getting access to the deeper tissue of the neurons and other glial cells. Okay, so this is simply a quick list of the neuroglia. We have astrocytes, number 1. Number 2, oligodendrocytes. Number 3, microglia. Number 4, ependymal cells. These are all categories of neuroglial cells in the central nervous system, right? These are all in the central nervous system. So we're talking about the blood and spinal cord itself. Do you have any questions at this time? Okay, gang, let's keep going. We're going to continue our conversation. We're going to switch gears and talk about the neuroglia cells we find in the peripheral nervous system. So remember, peripheral nervous system refers to all the nervous tissue that sits outside the brain and spinal cord. Okay. Neuroglia of the PNS, the peripheral nervous system. Okay. Well, first we have probably what is the most famous neuroglial cell. You know, most people know about this. This is the Schwann cell. Okay, Schwann cells. Let's see, if you want to look at Schwann cells, have a look at page 412, figure 12.7, or page 413, figure 12.8. Okay. All right. So, a bunch of things to say about the Schwann cells. They form the myelin sheath within the peripheral nervous system. They are, in fact, similar in the sense that they are analogous. Okay, they are similar, but they are not identical to the oligodendrocytes of the central nervous system. These cells are similar but not identical to the oligodendrocytes of the central nervous system. Okay, Schwann cells, one of the things they help to do, particularly in the, as they're located in the peripheral nervous system, is that the Schwann cells can actually help regenerate or heal damaged sections of axons. So, if you've experienced some sort of physical trauma in the past, maybe in a car injury or something, and there was some damage to nervous system tissue in your foot or your hand or arm, okay, the Schwann cells are capable of helping heal that damage as long as it's not too severe. So help regenerate damaged sections of axons. And Schwann cells themselves are actually capable of enclosing what are referred to as unmyelinated axons. Okay, so let me talk about that. Exactly what are we talking about here? Because it's a common misconception that that Schwann cells always form myelin sheath, and there's sort of an exception to that. There's a little bit of fine print in our advertising that we need to talk about. Okay, so let me type in this question here. What is myelin sheath? Let's talk about that. Okay, so myelin sheath, you can see myelin sheath on both figures 12.7 and 12.8 on page 413. Okay, myelin sheath is a multi-layered wrapping of a Schwann cell's plasma membrane around an axon. Okay, if you could imagine that you have a very long, Band-Aid, like a 12-inch long Band-Aid, and you started wrapping that around your finger, you imagine that if it's a 12-inch long Band-Aid, you could wrap around your finger many, many, many times and build up a thick cushion of material. Those things, those wrappings, are the myelin sheath, okay? If you have a single layer of Band-Aid around your finger, that's actually not considered to be myelin sheath, okay? So there's a bit of a subtlety there. Myelin sheath is a multi-layered wrapping of Schwann cells, plasma membrane around an axon. A multi-layered wrapping of Schwann cells, plasma membrane around an axon. Okay. The key here is that it is multi-layered. So I'm going to italicize that and underline it. Okay, italicize it and underline it. If it's multi-layered, if you have Schwann cells that are wrapping around an axon, like a huge Band-Aid wrapping around your finger and overlapping on top of itself multiple times, then yes, that is myelin sheath. But if you have a single wrapping, a single layered wrapping, that is technically not considered myelin sheath. Okay? So take a look. If you look on page 413, okay, just look at picture D. Picture D shows you a transverse section of unmyelinated axons. Yes, there is a Schwann cell there wrapped around, but it's wrapped around one time. So that's unmyelinated. Even though there's a Schwann cell there, that's unmyelinated material. But on picture C, you have a transverse section of a myelinated axon. Notice how much thicker the multiple wrappings of the Schwann cells actually are there. Notice how much thicker that myelin sheath really is. Okay? So that's the fine print in our advertisement. If you have a multi-layered wrapping of a Schwann cell, that is myelin sheath. If you have a single layer of Schwann cell, that is technically not myelin sheath. So Jennifer makes a statement on the chat window, I'm assuming about the myelin sheath, that it makes the impulses travel faster and keep homeostasis. Yes, Jennifer, that is correct. And we'll talk more about that in just a moment. Okay. Gang, are you okay right now? Is this making sense? Do you have any questions? All right, let's keep moving here. Okay, so we're talking about neuroglia of the peripheral nervous system. Number one is the big honcho. That's the Schwann cell. Number two, however, would be another category of cell called satellite cells. All right. Satellite cells surround the cell bodies of neurons of peripheral nervous system ganglia. Surround the cell bodies of neurons of the peripheral nervous system ganglia. Okay. They provide structural support to neurons. And they regulate the exchange of material between the cell bodies, okay, between the cell bodies of the ganglia and the interstitial fluid. Okay, and so you can see, that's not the best image, but you can see a little bit of a satellite cell on figure 12.7. Picture C of figure 12.7 on page 412, you see a satellite cell there. Okay, so you see a cluster of neurons are part of that ganglion. Okay, and so one of the cells there, your book is showing you as a satellite cell. That would also be considered a type of neuroglial cell of the peripheral nervous system. Okay, gang. Any questions at this time? Okay, please let me know if you have a question. Feel free to unmute your microphone and interrupt me. Feel free to type into the chat window. Okay, so we're going to go away from some basic cellular anatomy of the nervous system and start moving into the physiology of the electrical signals. So I'm going to give you, let's see here. I'm going to give you some basic background information, and then I'm going to show you a video on this. Okay, so we're going to start talking about the physiology of electrical signals. So this, as a topic, starts in page 414, spills over to page 415, and the next several pages of your chapter here. All right. Electrical signals in the nervous system. Okay, so first we're going to give you an overview and some basic background so that you can understand the conversation that we're going to have. Okay, number one, when we talk about electrical communication in the nervous system, please understand that there are two different types of electrical communication in the nervous system. Okay, there are two types of electrical signals in the nervous system. Typically, in very beginner level introductory courses, you will only focus on one type of electrical signal, but there are in fact two. We need to talk about both. Okay. The first form of electrical signal is called a graded potential. We'll be talking about these things in more details down the road here, but graded potentials are used for short distance communication. Okay. Used for short distance communication. Okay. And so as an example, okay, you know, what would we mean by short? You know, let's try to put some numbers on this. I would say the distance of communication would basically be about a few millimeters at most, okay? A few millimeters. Okay, a few millimeters is the scale of short in this definition here. Now, I don't want to, I mean, it is important that you know how big a millimeter is, okay? If we're going to be in science, we have to know these things. But I do know and recall from some experiences that students often don't really know what a millimeter is. So, you know, if you have a ruler at your house, you know, get that dusty thing off and look for millimeters. But if you really don't have a ruler at your house, let me give you an example of something. Okay, a 10-cent coin, a dime. Okay, we all carry change around in our pockets or pocketbooks. Okay, our wallets. The width of a 10-cent coin, a dime, is actually 17.9 millimeters. Okay, 17.9 millimeters. So, that doesn't look right at all. Well, at any rate, I'll check on that. But the width of a dime is, I might have that wrong. That might be 7.9 millimeters. At any rate, I'll come back to that. Hold on one second. Let's check that out. Oh, no. Width of a dime in the United States is 17.9 millimeters. Okay, I was questioning myself. That is in fact right. The width of a dime is 17.9 millimeters. So if you don't have a ruler, you can think about a 10-cent coin, a dime, and that is 17.9 millimeters. So certainly a graded potential would not travel any further than that. Okay, it definitely won't travel any further than that. And so as such, you're typically going to find graded potentials being used at the dendrites and the cell body of a neuron. Okay, and we'll talk about that in just a moment. The second type of electrical signal is an action potential. Okay, so this is the one that's most famous. People typically talk about it in other courses. This is used for long distance communication. Okay, and In this scenario, long could actually mean, depending on the axon and what, if it's an axon that's running from your hip down to your big toe, right, down your entire leg, depending on how tall you are, this axon could actually be over a meter, right? It could be over 39 inches long. So action potentials are going to be for long distance communication. Up to and beyond 1 meter is the scale of long here, okay? And think about the length of an axon down your leg, okay? So an action potential can be used for long distance communication. Graded potentials are used for short distance communication. Okay, please go ahead and ask any questions you may have. All right, number 2. Remember, when you have an electrical signal that's generated in muscle tissue, we call it a muscle action potential. But when you have the electrical signal being generated in the nervous tissue, which we're talking about nervous tissue here in chapter 12, then you call it a nerve action potential, okay? We talked in previous chapters about how skeletal muscle tissue can actually have muscle impulses. And so I want to be sure that you appreciate that. If it's happening in the muscle cell, it's a muscle action potential. If it's happening in the neuron, it's a nerve action potential. Okay, when an electrical signal is generated in muscle tissue, it's called a muscle action potential. When the electrical signal is generated in nervous tissue, it is called a nerve action potential, right? So while there are sometimes subtle differences between the characteristics of these electrical signals, they basically are the same. And what kind they are depends on what kind of tissue is actually creating or forming the electrical signal. Okay. Also, remember that action potentials are sometimes simply referred to as electrical impulses. Okay, action potentials can be simply referred to as impulses or electrical impulses. Number 4, the term membrane potential. Okay, membrane potential refers to the separation in electrical charge on 2 sides of a membrane. Right, in the context that we're going to be talking about, that membrane is the plasma membrane. Okay, it could be the plasma membrane of a neuron, could be the plasma membrane of a muscle cell. Nonetheless, it is a plasma membrane. So membrane potential refers to the separation of charge. Now, when I say separation of charge, I also mean the difference in charge, the separation or difference in charge in electrical charge on 2 sides of a membrane, right? On one side, on the outer surface of the membrane, you might have 50 positively charged ions. And on the inside of the membrane, you might have 10 positively charged ions. So that would be a difference, right? That would be a difference of 40. 50 minus 10 is 40. So the membrane potential refers to the separation or difference in an electrical charge on two sides of a membrane. Okay. Now, there's some other aspects to this phrase. Okay. When we talk about the difference, remember that the greater the difference, the more likely ions will move across the membrane. Okay, the greater the difference, the more likely ions will move across the membrane. Okay, the more likely those ions will move across the membrane, the more likely it is that the ions move across the membrane, the greater the membrane potential. Okay, let me put an arrowhead there. Okay, the greater the difference, the greater the difference, the more likely ions will move across the membrane. This means you have a greater membrane potential. Let me bring up a schematic here or do a little bit of drawing to try to be sure that you're okay with this. And I will be coming back to the Word document, so if you didn't get all that drawn or typed out, that's okay. Okay. All right, so let me use an analogy here to talk about membrane potential. Okay, let's see here. Okay, what I'd like you to envision for a moment, if that is, if you were looking at a house from the side, okay, if you were looking at the side perspective of a house, so we might have a house here, okay, and the bottom here, all right, would be the base of the driveway. And so we might have a driveway that has that slope. Okay, so here's house A, and over here is house B. So we're going to look at a different house from the side. And you look at that slope. Okay, so please let me type a question into the chat window. Does house A or B have the greater slope to the driveway? Okay, Jennifer, how about the rest of you? Do you remember what slope is from your math class days? Okay, thank you, Ashley. All right, absolutely. House B has the greater slope. Okay, so think of it this way. Okay. If we mark the top of the driveway and the bottom of the driveway with red lines, you notice that house B has the greater slope because the distance between these red lines is greater in house B than the distance between the red lines in house A. In other words, the difference between the red line positions is greater in house B than it is in house A. Okay, the difference is greater. So let me ask you this. If I had a tennis ball, if I had two tennis balls and I positioned them at the top of the driveway of each of these respective houses, okay, and if I held them into position by, this imaginary hand, and then I took my hand away and let gravity work on these tennis balls, which tennis ball, that of house B or house A, which tennis ball is going to more aggressively roll down the hill? Okay, it's B, isn't it? It's house B. So think about that. The ball on house B is going to roll down because there is a greater difference. There is a greater difference between one side of the membrane and the other side of the membrane. Okay, so I need to have another color here. Okay, so if we think of this as the outside of the plasma membrane and this as the inside of the plasma membrane, the outside of the plasma membrane and the inside of the plasma membrane, the greater the difference in electrical charge, the greater the difference in electrical charge, the more likely the ions are to move. In other words, the more likely the tennis ball with house B is going to move. That's what membrane potential is measuring. Membrane potential measures the difference in electric charge between the inside and outside of the plasma membrane. The greater that difference between the inside and the outside, the greater the membrane potential, the greater the ions are, the greater likelihood the ions are to move across the membrane. Okay, so question coming out. Does membrane potential make sense? Are you with me? I don't want to go any further until you tell me that you're comfortable with this. Folks, are you understanding membrane potential? Okay, I'm not getting responses, so I think you're not understanding membrane potential. Okay, let's continue. Let me try to do this a different way then. All right. So Pamela is asking, does the difference is due to a higher concentration of ions? So let me try this. Okay, we'll stay with our house analogy. But now let's talk about this. Let's say that I have a plasma membrane here for house A. Okay, so we're going to say that this is plasma membrane. Okay, and I'm going to compare the analogy of house A to house B. Let's say that here is the outside of the plasma membrane, and here's the inside of the plasma membrane. And that's true for both the A and B analogies. Let's say that on the house A analogy, I have 50 positively charged ions outside. And let's say inside I have 40 positively charged ions inside. So, question coming through the chat window. In the house A scenario, when I'm talking about the bottom example with the ions, what is the difference in ion concentration comparing the outside to the inside? Okay, Matteo, thank you. There's 10. That's exactly right. So the difference here, okay, just to be explicit and write this out, is 50 minus 40 equals 10. You got it. Let's do the same thing over here in house B. Let's say that there's 50 positive ions outside and there are 20 positive ions inside. That difference is going to be what? Type it into the chat window if you know what the difference is at this time. Good, okay. 50 minus 20 is 30, absolutely. Okay, now let me ask you something. Stay with your analogy here, okay? Isn't 30 greater than 10? Isn't this difference where I'm highlighting right now, isn't that difference greater than this difference? Isn't the difference of the house B analogy greater than the house A analogy? That means that the membrane potential, okay, so 30 would be the membrane potential for house B or cell B. And that membrane potential or difference that we've calculated tells you the steepness of the driveway. The more likely it is for the ball to roll down the hill is greater in house B than house A because the difference in membrane potential here is greater. Okay, 30 is a bigger difference than 10. So that means that the imaginary tennis ball in house B is going to more aggressively move down the hill. And in house B, the analogy here, the ions on house B are going to more forcefully move across the membrane. Okay, there's going to be a greater movement of ions across this membrane in the B analogy than in the A analogy because the steepness of the driveway, the difference in the membrane voltage, is greater here at 30 than it is here at 10. Okay, let me ask again. Is membrane potential making sense? Okay, all right, good. All right, that's much better. Okay, and it's okay to tell me no. Ashley asks, so would the flow of ions stop once both sides are equal? Theoretically, yes, Ashley, but that really doesn't happen for any long period of time until you pass away. Okay, I mean, if you pass away, then the voltage is going to drop to zero. The difference is going to be zero. The membrane potential will be zero because you're dead. But as long as you're alive, that membrane potential is not going to be zero. Okay, other questions? Okay, all right, that's good that we stopped to do that. Let's continue. Let me go back to the Word document. And remember, we tried to illustrate this in the PowerPoint. Membrane potential refers to the difference in the electrical charge on two sides of the membrane. The greater the difference, the more steeper the slope of the driveway, the more likely ions will move across the membrane. Okay? The greater the difference, the greater the membrane potential. Okay. Next point, number 5. Okay, ion channels. Okay, these ions that have to move back and forth across the membrane, the only way you get them to move back and forth across the membrane is to have these protein channels that are known as ion channels. You see various kinds of ion channels on page 417, figure 1211. Okay, ion channels. These are channels, or I'll use the word tunnels. These are tunnels that are made of protein that allow ions to move across the membrane, when I say membrane, you understand I'm talking about the plasma membrane, to move across the plasma membrane down their electrochemical gradient. Okay, so let's talk about that little buzz phrase in there called electrochemical gradient. Okay, this refers to a gradient. A gradient is an area of difference, an area of difference. Right, never use, when you're defining a word, never use that word in its own definition. And I appreciate that, okay? This is an area of difference, okay? I might think about your own yard. You might have an area that's more elevated than another area, right? So whenever it rains, the water flows down the slope of your yard from high to low. That entire slope is a gradient. It's an area of difference in elevation of your yard. So an electrochemical gradient is an area of difference that has two characteristics, okay? Because we're talking about an electrochemical gradient, okay? It has two characteristics. One, electrical in nature, and the other, concentration. Okay? For example here, if one side of a membrane has 100 sodium ions, Na+, if one side of a membrane has 100 sodium ions and the other side has 25 sodium ions, then sodium will flow. It will physically travel toward the side with fewer sodium ions. And that's because of the difference in concentration. Okay, in other words, that's the chemical gradient aspect of it. Towards the side with fewer sodium ions because of the difference in sodium ion concentration. That's the chemical gradient that we're talking about, okay? Now, I have to continue this. This is sort of a big, long run-on sentence, but I don't care about the English. I care about the science. And, okay, so part 1 here. If one side of a membrane has 100 sodium ions and the other side has 25 sodium ions, then sodium will move toward the side with fewer sodium ions because of the difference in sodium ion concentration. The difference in concentration is referring to the chemical gradient that's part of the electrochemical gradient term. But there's also the electrical part. So we continue our idea here. And the fact that there is much less positive charge on the side with 25 sodium ions. Okay, there's simply less positive charge in an area where there's only 25 positively charged atoms. And the fact that there is much less positive charge on the side with the 25 sodium ions than the side with the 100 sodium ions. This refers to the electrical gradient. Okay. So the concentration of ions is the chemical gradient part of electrochemical gradient. And the status of the charge, the amount of charge energy, 25 on one side of the membrane versus 100 on the other side, that's the electro part of the electrochemical gradient. Let me continue here. Okay. If the same situation existed as I've immediately defined in Roman numeral I, immediately above. If the same situation exists in number I above, but now there are also 25 potassium ions on the side with 25 sodium ions. Sodium will still move towards the side with fewer sodium. Okay. If the same situation exists in I above, but now there are also 25 potassium ions on the side with the 25 sodium ions, the sodium ions will still move towards the side with fewer sodium, but not as rapidly because there is less difference in electrical charge. Okay? There's less difference in electrical charge because one side has 100 positive ions and the other has 50 positive ions. Okay? Folks, in part Roman numeral 2 here that I'm shading in gray at this time, do you see in part number 2, do you see that the concentration of sodium ions has not changed? The concentration of sodium ions has not changed between the bottom scenario and the top scenario. Okay? Let me put this down. Notice how the concentration of sodium has not changed, but the amount of electrical energy has changed because of the positive potassium ions that have been added to the example. That's why electro and chemical gradients are similar, but they're not exactly the same thing. Am I making sense here? Are you with me, gang? Is this making sense? Take time to read these sentences for yourself a little bit. Does it make sense? I'm not seeing a response. So okay, so Mateo, so the electrical gradient doesn't change the side that the ions move to. Generally, no, Mateo, but it does change. Yes, it changes how fast the ions will move. Okay, it can do that, right? It can do that. Absolutely. Do we need to go to PowerPoint on this and diagram this out? Please let me know how I can help you at this moment. Will potassium also move across the membrane along with sodium? Ashley, potassium does have the possibility of moving, but it's going to be moving potentially through a different protein channel. But yes, it can move. But please understand, Ashley, even though it can move, it very likely will move at a different moment of time. Okay. All right. Okay, anything else you'd like to ask? Okay. Come back next class. We're getting a little short in time. Come back next class and tell me if you need me to cover this again with you. If you need me to draw it out for you, I will do that. But right now, I'll assume that if you spend a little bit of study time with it, that you can understand this. Okay. Let's talk about the different types of ion channels that exist. Okay. So let's see here. I'm going to go to letter B and say types of ion channels. And so, okay, this is where page 417, figure 1211 will be very important that you can study this. Okay. And so we have leak channels, right? Leak channels randomly change between open and closed positions. Randomly change between open and closed positions. Okay. Now, by random, we mean is that we have no way of predicting when these things will open and close. It doesn't mean that there isn't something controlling it. It simply means we cannot predict it. Okay. So random doesn't mean it's not intentional. It simply means it's not predictable. Okay. So with leak channels, let me mention that typically the plasma membrane of neurons, or in cells in general, to be honest with you, plasma membranes typically have more potassium ion leak channels than sodium ion leak channels. Okay, the plasma membranes of cells typically have more potassium ion leak channels than sodium ion leak channels. And it is also true that if we were to compare an individual potassium channel leak channel to potassium sodium ion leak channel, that the potassium ion leak channel is leakier than the sodium ion leak channel. In other words, if we only had two leak channels, one of them potassium, the other one sodium, a potassium leak channel might allow 3 ions of potassium through, while a sodium leak channel would only allow 1 ion of sodium through in the same amount of time. Okay. Each potassium channel tends to be leakier than each sodium channel. Okay, tends to be leakier. Okay, it's kind of like having 2 rowboats out on the lake. Which one of them is leakier? Which one allows more water into the rowboat than the other in the same amount of time? Well, the potassium rowboat allows more water into the rowboat than the sodium rowboat. Okay. All right, that's the first kind of channel. The second kind of channel is a ligand-gated channel. Ligand-gated. This refers to opening, okay? In the ligand-gated channel, these channels opens due to the binding of and closes due to the detachment of so let me start the sentence. It opens, ligand-gated channels opens and closes when a specific molecule that molecule, I could say the word chemical, I could say the word ligand. Okay, a ligand is simply a molecule. A ligand is a chemical, it's a molecule, it's all the same thing. A ligand is a molecule, and of course a molecule is made of atoms that link together. That's chemistry. So a ligand-gated channel opens and closes when a specific molecule, a specific chemical, a specific ligand, such as a neurotransmitter, hormone, or other molecule, okay, opens and closes when a specific molecule, such as a neurotransmitter, hormone, or other molecule, binds or leaves the channel, okay? Opens due to the binding of, closes due to the attachment of, when a specific molecule, chemical, or ligand, such as a neurotransmitter, hormone, or other molecule, binds or leaves the channel. Okay. Third type of channel is a mechanically gated one. Mechanically gated channels opens and closes in response to vibration, touch, pressure, or the stretching of tissue. And to complete your notes, we also have those famous channels that we've already talked about in this course, because we emphasized it when we talked about the neuromuscular junction, is the voltage-gated channels. Okay, voltage-gated channels open and close in response to a change in membrane potential. Open or close in response to a change in membrane potential. All right, so I know there's a lot of new ideas that we're focusing on right now. It might take some time to get comfortable with it. Do you have any questions right now? Okay. All right. So my next desire is that I could show you a video, but I'm not going to have enough time to, because we're already an hour and 15 minutes into the class here. So gang, here's what I'd like you to do over the next day and a half is to dig very deeply into the portion of chapter 12 that talks about action potentials, because this is what we're going to be talking about all next lecture. So the more you dig into it, the easier it will be for you to follow the lecture next time. Okay? Before we, we're gonna take about a 15-minute break, and I will be back online for the office hour. I will be giving out answers to your lab exercise homeworks that were technically due today if we were running together. And so there will be some things that would be beneficial for you if you can hang around. Otherwise, you can watch it on the video. But at any rate, I will be back online to help you. So a couple questions here. Pam asked if I can email the video that I'm going to show. Yes, Pam, I can do that, and I will do that. And are we going to go over the lab homework on Wednesday? Yes, I can. I will go over it today and on Wednesday, so I will do it both days. Okay. Folks, before we take a quick break, do you have any questions right now? Okay. Then I'm going to stop sharing my screen, and I will be back online with you at 9:30 if you want to stick around, and we can talk about your lab homework, and I can help you with other things that may be on your mind, any questions you might have. So I will see you in about 14 minutes now at 9:30. I'll see you soon. Okay, gang, welcome back. So thank you for hanging around here. It does seem that each class we're getting fewer and fewer people attending, and that's always concerning because I'm not sure how well people are able to keep up with the new stresses that are on everybody. So do your best you can to stay focused and to encourage your friends that you may be in contact with in class to also keep up with their study efforts. So let's take a look at your homework that would be due today, which are lab exercises 16 and 17. Okay, let's start with lab exercise 16. Okay, this was on nervous tissue in the lab manual. Let's take a look at reviewing your knowledge, page 273. Okay. Okay, so let me read this little paragraph here and I'll fill in the answers for section A as we go. If you touch a hot stove with your hand, the number 1 sensory receptors in your hand send a signal of pain to the CNS, the central nervous system, through the number 2 afferent with an A, A-F-F-E-R-E-N-T, through the afferent axons of the peripheral nervous system. Number 3 is peripheral. When the information reaches the central nervous system and is processed, number 4, motor response is sent through the number 5, efferent, E-F-F-E-R-E-N-T, axons of the peripheral nervous system to skeletal muscles that are number 6, effectors. So all of the answers for part A are number 1, receptors, 2, afferent, 3, peripheral, 4, motor, 5, efferent, 6, effectors. Do you need it? If you need any of that repeated, please type into the chat window. Okay. Section B, nervous system tissue. Okay, supporting cells of the peripheral nervous system, number 1 and 2 are satellite cells and Schwann cells. Numbers 3, 4, 5, and 6 are astrocyte, epidermal cells, microglia, and oligodendrocytes. 7 and 8 are oligodendrocytes and Schwann cells. 9 and 10 are astrocytes and satellite cells. Turning the page to page 274. Number 11 is neuron, 12 epidermal cells, 13 microglia. Do you need anything from section B repeated? Letter C, structural classification of neurons. Number 1 is a multipolar neuron. 2 is a bipolar neuron. 3 is a unipolar neuron. 4 is a bipolar neuron. Section D, functional classification of neurons. Number 1 and 2 are motor neurons and interneurons. Numbers 3 and 4 are also motor neuron and interneurons. Number 5 is a sensory neuron. 6 is an interneuron. Do you need anything from part C or D repeated? Okay. Letter E, myelination of axons in gray and white matter. Number 1 is letter B, white matter. 2 is A, gray matter. 3 is C, myelinated fibers. 4 is D, unmyelinated fibers. 5 is E, nodes of Ranvier. Okay, gang, anything from reviewing your knowledge that you need repeated? Okay, let's go to page 275, using your knowledge, conduction of a nerve impulse. Okay, hopefully this is supporting your reading of chapter 12 in the textbook, because a lot of this is very relevant. Okay, number 1, section A, conduction of a nerve impulse, page 275. Number 1 is dendrite. 2 is cell body. 3 is axon hillock. 4 is trigger zone. 5 is axon. 6 is axon terminal. 7 is synapse. And 8 is the second neuron or effector. Okay, so this is very important. Okay, you're reordering the following parts in the correct order of receiving and sending the nerve impulse. Okay, so number 1 is dendrite, 2 cell body, 3 axon hillock, 4 trigger zone, 5 axon, 6 axon terminal, 7 synapse, 8 second neuron or effector. Any questions? Okay, letter B. Talking about nervous system tissue and diseases. Okay, identify the nervous tissues that are involved in the following disease. Number 9, multiple sclerosis, many of you know from other courses, is due to a demyelination of the neurons of the brain and spinal cord. Multiple sclerosis is a disease associated with damage to the myelin sheath. Number 10, epilepsy. Well, honestly, we don't truly know in great detail what's causing that, but we do know that epilepsy is due to an electrical storm in the brain. So the malfunction is with the neurons of the brain. But exactly what's wrong, we truly don't know. Letter C at the bottom of page 275, overview of communication within the nervous system. Okay. All right. So I'm going to read the answers and then we'll talk about this. Number 1 is graded potential starts in a sensory receptor in the skin. Your next statement, which starts with the words at a second synapse, that's number 5. The next page, page 276, the statement that begins with the graded potential, that's number 2. The next statement that starts with the lower motor neuron, that's number 8. The next statement, in another synapse, that's number 7. The next statement, which starts with a primary interneuron, that's number 4. The next statement, a stimulus from the brain, is number 6. And the final statement at the first synapse is number 3. So, let me read the statements in the correct order of events. Okay, so number 1, graded potential start in a sensory receptor on the skin. Number 2, the graded potential triggers an action potential in a sensory neuron. Number 3, at the first synapse, a presynaptic sensory neuron stimulates a postsynaptic interneuron to form a graded potential in the cell body, followed by an action potential. Number 4, a primary interneuron forms an action potential and crosses to the opposite side of the brain. Number 5, At a second synapse, a graded potential followed by an action potential occurs in a secondary interneuron, which reaches the cerebral cortex. Number 6, a stimulus from the brain causes a graded potential and then an action potential to form in an upper motor neuron, which crosses back to the original side of the body. Number 7, in another synapse, the neurotransmitter creates a graded potential, which triggers an action potential in the lower motor neuron. Number 8, the lower motor neuron forms a neuromuscular junction with the hand muscles, which causes the muscles to contract as the man writes the letter. Okay, so the whole purpose there, gang, is to get you to kind of understand the series of events that must occur for your brain to control how your hand writes a bunch of notes. Questions at this time? Okay, let's go to exercise 17. Reviewing your knowledge, exercise 17. And that would be, okay, page 283. Page 283, letter A, the meninges. Here we go. Number 1 is the arachnoid motor. Number 2 is the dura mater. 3 is the epidural space. 4 is the pia mater. 5 is the subarachnoid space. 6 is the extension. 6 is the denticulate ligament. The denticulate ligament. Okay, do you need any of that repeated? Okay. Ashley, I missed your statement from last time. 3 was at the first synapse of our previous activity. Let me back up and see. I think that is correct. Yes, Ashley, 3 was at the statement in the beginning at the first synapse. That is correct. Okay, so page 7, page 283, reviewing your knowledge, section A, meninges. Any questions? Okay, section B, spinal cord structures. Number 1, gray matter. 2, the posterior median sulcus. 3, the gray commissure. 4, the posterior root, which is also called the dorsal root. Number 5, the conus medullaris, the conus medullaris. 6, the anterior root, which is also called the ventral root. 7, the posterior root ganglion, which is also called the dorsal root ganglion. 8 is the cauda equina, cauda equina. 9 is white matter. 10 is the anterior gray horn. 11 is the central canal. 12 is the cervical enlargement. 13 is the anterior median fissure. 14 is the filum terminale, and 15 is the lumbar enlargement. Okay, a lot of funny words in there. Do you need anything from part B repeated? Number 7, okay. Number 7 is the posterior root ganglion. The posterior root ganglion. Okay, anything else? Okay, gang. Let's go to using your knowledge, page 285. Using your knowledge, page 285. Section A is the spinal cord, a transverse section of the spinal cord. Number 1 is the subarachnoid space. Number 2 is the posterior root, also called the dorsal root. Number 3 is the anterior root, also called the ventral root. 4 is the dura mater, and if we're being honest, it's the dura mater and the arachnoid mater. Number 5 is the pia mater, and 6 is the epidural space. Okay, that's the epidural space, which is going to be typically filled with a bunch of fatty tissue, adipose tissue. Okay, so that's letter A. Do you need any of that repeated? Okay, letter B on page 286. Okay, number 7 talks about the polio virus and how it can cause muscle paralysis. Number 7 says identify the area of the spinal cord that is destroyed by polio virus. That would be the anterior horn. Number 7 is anterior horn, which you may say as ventral horn. Number 8 talks about shingles. It's caused by a virus called herpes zoster virus. Okay, the same thing that causes chickenpox. The area of the spinal cord that is damaged is the posterior root ganglion. The posterior root ganglion, which is also called the dorsal root ganglion. Number 9, identify the structural classes of neurons whose cell bodies are present in the spinal cord. Well, in the spinal cord, that would be the number 9 is multipolar neurons. Number 10, nerve fibers are classified according to their diameter and presence or absence of myelin sheath. Okay, so all 3 nerve fibers types are found in the anterior root, and classes A and B fibers in the posterior root. So for the anterior root, all 3 nerve fiber types are present. In the posterior root, only classes A and B are present. Number 11, okay, you remove cerebrospinal fluid. Explain why spinal taps are not done. Okay, you remove cerebrospinal fluid by inserting a needle below lumbar vertebrae L2. Explain why spinal taps are not done above this level. Well, simply it's a matter of you don't want to damage the spinal cord with the needle, right? You don't want to accidentally hit the spinal cord with your needle, so you always go below lumbar vertebrae L2. Okay, gang, any questions for part B? All right, then letter C, pathway of sensory and motor impulses. Number 12. Okay, so for numbers 12 through 16, we are numbering numbers 1 through 5. We're indicating the order of the structures through which sensory impulses pass. Okay, number 12 would be 2, 13 would be 3, 14 would be 4, 15 would be 5, 16 would be 1. Do you need any of that repeated? Okay. And then 17 through 20, we're also numbering 1 to 4. 17 is 4, 18 is 1, 19 is 2, 20 is 3. All right. So Ashley or Jennifer, any part of that that you need repeated? Jennifer, why didn't we go over part B 1 through 15? Do you mean, let's see here. Oh, I see. I'll have to get back to you on that, Jennifer. My notes don't include those right now, so I'll get back to you that. I'll have that for you on Wednesday. Okay. Other questions? Okay. All right. So, Jennifer, is there anything else that I can help you with? Okay. What do you need help with? All right. Okay. So the spinal cord cross section. Okay, I guess that's relevant. And you were asking about page 284. The spinal cord cross section is not going to be in the software, but you get an idea that, you know, for example, you have work on page 280 and 281 of your lab manual that talks about that. And then let's see if we can find a relevant position in your textbook on that. Okay, so bear with me a moment. And I appreciate you pointing that out to me at this time. Okay, so I would say, Jennifer, have a look at in your textbook on page 448. And there you will see picture B at the bottom. Okay. That definitely gives you a nice cross section of the spinal cord as is part of the cervical vertebrae there. Hopefully that will help you answer some of the questions that you have. Yeah, we're not. Okay, so we're not actually covering, unfortunately, we don't have time to cover chapter 13 in lecture. There's just not enough time. So there's a little bit of hunting and pecking you have to do on your own to answer some of these things. But, you know, as I look at chapter 13, page 448, page 450, and page 451, I think will allow you to easily answer some of your questions at this time. And so what you might expect on a potential lab exam would be an image similar to any of those textbook images with a couple arrows drawn either to the white matter or the gray matter or something like that. Okay. Is there something else that you need help with at this moment? Okay. Are there, you had mentioned earlier in the chat about other anatomy of visible body. Are you okay now with the scleral venous sinus? Or is it something you think you can find? Okay. Let me know again if you can't. And definitely don't forget about, even though, even if you have to, there's nothing wrong with going to Google Images and typing in scleral venous sinus and looking at what the Google image is showing you, and then using the software to locate that in the anatomy. I'm 99% sure that visible body does have the scleral venous sinus, so it should be locatable by you. Okay. All right, Jennifer, anything else I can help you with today? All right. Then please take care of yourself, okay? And I'll see you on Wednesday. Okay, bye-bye.